Hi students, for the second video for online lecture 18 and chapter 10, we are now going to talk about some of the calculations that are going to come with our work. So let us begin with enthalpy. As we saw in the last video, we got talking about the first law of thermodynamics and our internal energy. Our internal energy was the sum of our heat plus our work. So at a constant pressure, you are going to come to find out that Q is actually equal to delta H, which is going to be called enthalpy. This is a value that we will see in a balanced chemical equation here by the end of this chapter. And our work is going to be equal to our negative P delta V that we saw in our expansion and compression discussion in our previous video. So now we are going to substitute those values in and get delta U equals delta H minus P delta V. A better way of explaining this is that our enthalpy is equal to our internal energy plus P delta V. What that is just a reorganization of the previous equation. We are going and taking our delta H to the other side and changing the sign for all of our various variables. So let's go ahead and take a look at some of this math. A certain gas expands in volume from 2.0 liters to 6.0 liters at a constant temperature. So let us go ahead and first look that our 2.0 to 6.0 is going to be an expansion. Remember that if our volume is going to be getting bigger, we would expect for our work to be considered negative. So how do we do this? Well, let's go ahead and look at what they ask. Calculate the work done by the gas if it expands against a vacuum. An important part about a vacuum is to let you know that there are 0 atmospheres of pressure in a vacuum. The atmosphere, which we will see in our next chapter when dealing with gases, is the SI unit for pressure. So now what we can do is state that our work is equal to negative P delta V, but now we are going to say negative our pressure being 0 atmospheres times our change in volume, which is going to be final minus initial, and you will see that I am going to end up with a value of 0 liter atmospheres of work. This is because it takes no work to fight against a vacuum. That is not going to have a pressure pushing against us while we try to accomplish that volume change. So let us go ahead and look at B. We are now going to use the same equation of W equals minus P delta V, but now this time we actually have a pressure. So we are going to state that negative, our pressure being 1.2 atmospheres that we must fight against, and we are going to use the same change in volume. So we have our 6 liters minus our 2 liters, and that is going to be a change of volume of 4 liters. So if I put this into the calculator, I am going to get a work value of negative 4.8 liter atmospheres. Now, liter atmospheres is not a useful unit for us because we do not know where that quantifiably sits with our other energy units. So what we are going to do is now convert the liter atmosphere to our joule. In order to do that, we will state that there is 101.3 joules for every 1 liter atmosphere. You are expected to know this unit conversion. If that is the case, we are now going to see that our work that we actually calculate is a negative 486.2 joules. This will allow our work to be compared to our enthalpy and we will have the same units. So when doing problems such as this, make sure that one, you have a pressure that is consistent so that you can do this math. And then once you have your change in volume, we must go and convert from our liter atmospheres to joules so that we are able to use it in our first law of thermodynamics. Now we must go and compare our delta H and our delta U. So now you will see that I have this balanced chemical equation. From this point forward, our delta H is going to be put after our balanced chemical equations, and you will now see a sign convention placed with it. If the sign is negative, this means that this is energy being released and will be an exothermic reaction. If it is positive or there is no sign written, this means that it's an endothermic reaction and that energy is needed. We are not going to put our delta H's into our balanced chemical equation. We put them off to the side with the correct sign convention. But now what we want to look at is what happens during this reaction. So we're going to look at our internal energy, which is equal to our delta H minus P delta V, and at 1 mole of our H2, that has a volume of 24.5 liters at 1 atmosphere. So what we are going to do is convert our P delta V using what is going to be known as the ideal gas law, which you will see in the next chapter. And our P delta V will now become equal to delta N RT. So what does that mean for us? That our delta U is going to be equal to our delta H, which you see here, and we have now plugged that value in there. And then finally, we are able to take our 2.5 kilojoules from our delta nRT and immediately plug it in here. This means that we are going to get a change in internal energy of negative 370 kilojoules. So what does this mean? Well, we are going to have major and minor contributors when dealing with our energy. Notice that our delta H is historically going to be our major contributor. When dealing with our internal energy, the lion's share of our energy is going to come from our enthalpy. Then our minor component is typically going to be our work. So no matter how much work you end up doing, it will only typically contribute a little bit of the energy that we are going to calculate. So now you can see what happens when I do this reaction in real life. Notice that it's going to come off in a shower of sparks, and as we are releasing all of that energy, which is going to be my delta H, we are going to have the change in volume by the expansion of that hydrogen gas and air and water vapor, causing all of this to expand. So what does this mean for us? Well, now we need to be able to go and do this calculation because our negative P delta V can only get us so far when dealing with our big reactions. We want to be able to look at balanced chemical equations and have useful calculations for energy. So let's talk about that in the terms of enthalpy. This is used to quantify the heat flow into or out of a system in a process that occurs at constant pressure. So the first clause that we must have in order to calculate enthalpy is our constant pressure. That allows us to then quantify our heat flow. In this case, our delta H is products minus reactants. These would be values that we could find in our textbook. A delta H is the heat given off or absorbed at a constant pressure. So now we can go and look at these processes. Notice that if we have our reactants going to our products, as you see here, notice that our delta H of the products is less than that of the reactants. This means that our delta H is going to be less than 0, or a better way of putting it, it's going to be negative. So this is nice that if you see a downward arrow now when dealing with enthalpy, you are seeing an exothermic reaction. Finally, if we go to the other side and you see our upward pointing arrow, you will now notice that our products have more energy than that of the reactants. So if we were to do products minus reactants, we will get a positive value, and this would be an endothermic process. This is going to be able to help us calculate many different reaction energies over the next couple of lectures. So now let's go ahead and look at this example. Calculate the change in internal energy when 2 moles of carbon monoxide are converted to 2 moles of carbon dioxide at 1 atmosphere and 25 degrees C. So what I need to do is go and put in my original equation. So now that we know we are at constant pressure, we are able to say that delta U is equal to our delta H minus our delta N RT. So let us go ahead and try to identify all 4 of these variables. So the first thing that we see is we have our delta H. It is done here in kilojoules per mole. But the important part is that our second term is actually going to be calculated in joules. So it is best for me to go and calculate and convert our delta H to joules per mole to start off. So this means that I would end up with negative 566,000 joules for our delta H. So now what we need to do is go and calculate our delta N. Our delta N in this case is going to be moles of gas in our products minus the moles of gas in our reactants. In this case, we are only going to use moles of gas. If it is any other phase, you do not put it in this calculation. So if we go and look for our delta N, I have 2 moles of gas in my products. So that is going to be 2. And my moles of gas and reactants, you will see that I have 2 here. And I would have 1 more coming from my oxygen. So this is going to be 2 minus 3, which equals -1. So now what I will do is put -1 here in for my delta N. What is R? This is going to be one of the 2 forms of the ideal gas constant. This value is going to be 8.314 joules per mole times Kelvin. We will see the other form in the next chapter. Then finally, what we need for our temperature is going to be our temperature. But now you can see that I have Kelvin in my units of my ideal gas constant. This means that I must convert my Celsius to Kelvin. How do I do that? Well, we'll take our Celsius and add 273. So that will give us 298 Kelvin. So now that I have done that, I am able to go and do all of this math, and I would get a result of my delta U being negative 563,500 joules. So what does that mean for us? Well, we are going to go and put that in a much better useful format and end up getting negative 564 kilojoules per mole of internal energy for this reaction. So as you can see, using the balanced chemical equation and our change in moles, we are able to calculate so much more than just using our pressure and a change in volume. Let's try one more example. Given the following thermochemical equation and their corresponding enthalpy, you see here that we are going to convert methane to CHCl3. Then what we need to do is calculate the change in internal energy for this reaction if 3 moles of my methane are converted with 9 moles of my chlorine gas. So what we need to do here is look at our delta U equals our delta H minus my delta N RT. So the first thing that I want to do is go in and plug in my delta H. You will see that value right there, and that is going to be negative 305,300 joules of energy. So then let's go ahead and get our minor term. And now we need to go and calculate the delta N. So in my products, you will notice that I have 4 moles of gas. If I go and look at my reactant, you will see that I have 4 moles of gas. So what does that mean? Well, if I go ahead and do the math of 4 minus 4, I actually end up with a 0. So this means that I can go in for my delta N and put in 0, and no matter what the value of R and T is, won't my second term be 0 based off of the multiplication of that term. So now our whole second term is going to be 0. This means in this case that our change in internal energy is just directly associated to our delta H. So we could state that the delta U for 1 mole of this reaction is actually going to be our original value of negative 305.3 kilojoules. But this is not the answer, because if you'll notice that I have 3 moles of my methane, but this reaction is only listed as 1 mole. So what can I do? Well, what you're going to do is you are going to need to multiply your delta H by 3. So I can say 3 times my delta H of this reaction is going to give me my change in internal energy. So what I will get in this case is negative 915.9 kilojoules of energy. So if I look at my answers on the left, you will see that I will get answer C. In this video, we use the fundamentals that we discussed in the first part of the lecture, and we were able to now look at it talking about enthalpy, which now means that we can figure out the energy at a constant pressure. But now in this second half of the video, you've been able to see how we can calculate the internal energy either gained or lost for a reaction using the balanced chemical equation and the ideas of the ideal gas law. Have a great day.